This video is about 2.3 in Stein's elementary number theory book. In general, 2.3 is about how to quickly compute inverses and huge powers. And in this video, we're going to talk about quickly computing inverses. So recall that to talk about the inverse of an integer, say mod n, we're trying to solve this congruence. A times x is congruent to 1 mod n. Now remember what that says is that a and x are inverses of each other mod n, since they multiply to 1 when you reduce mod n. And we want to know how do we compute that? So how do we solve this congruence quickly, say by hand? And so in particular, we're only talking about the case that this a and n, the modulus, are relatively prime to each other. Because in that case, that's when we know, by proposition 2.1.13, if you scroll back, that this congruence has a unique solution. In other words, that is exactly when a has an inverse. And in particular, remember that says that a is a unit mod n. So maybe it's hard to keep track because there's a lot of different ways to really say the same thing. The first thing we're going to look at to help us on our journey for how do we solve this equation quickly is the extended Euclidean representation, which tells us if you've got two integers and if you let g be their greatest common divisor, then you can find two integers, x and y, such that g is a linear combination of a and b. So x and y are like these coefficients that you can multiply a and b by respectively, and they add up to g. So in particular, let's just go to the proof of it. Let's let g be the greatest common divisor of a and b. Then what happens when you divide a and b by g? Well, then what you have left shouldn't have any common factors. So if you think about trying to divide 12 and 9, their GCD is 3. When you divide that stuff by 3, you get 4 and 3, and their GCD is 1. So they don't have any common factors. So whenever you divide a and b through by the greatest common factor, what you have left, in other words, a over g and b over g, they're co-prime to each other, or relatively prime to each other. So what we're going to look at then, well, if these two things are relatively prime, then what happens when I plug in, a over g, where this is, and my n, let's let n be b over g. Then I know that this congruence should have a solution. So in particular, this congruence is guaranteed to have a solution, again, because we just said that these two numbers are relatively prime to each other. Right? It satisfies this condition right here with a over g and b over g instead of a and n. So in particular, there exists a number x that makes this congruence true. So what we'll do is we'll clear fractions. Let's multiply both sides by g. So that would clear the g out of both of these, right? And you'd get that ax is congruent to g mod b. Think about what that says. Like, what is this equivalence relation on the integers? What does it mean to reduce something mod b? Remember, that says that b divides the difference ax minus g, right, when you move that to the other side. So in particular, there's some number y such that b times y is equal to ax minus g. So we'll write it this way, and it was convenient for us to just write minus y instead of y. Doesn't really matter. The only reason we use a minus y here is just to make it work out so that when I add g to this side, and now I could add this to the other side, I get this pretty ax plus by is equal to g. And remember, that was what we were after. So we can always express the greatest common divisor of two integers as a linear combination of those two integers. So let's look at, remember the division algorithm, and remember how we use that to find the greatest common divisor of two integers. And so what we're going to ignore for a second is this. And all I want to focus on is, if I want to compute the greatest common divisor of 5 and 7, remember what I would do is I would just divide 7 by 5. And I see that I can always write it in this form: a is equal to bq plus r. And in my case, a is 7 and b is 5. And then what I'm going to do, remember the algorithm to find the GCD, was to just shift this. So that I'm going to make this my new A, and I'm going to make this my new B. Or actually, it should go right here. And I'm going to keep doing that until, well, I can't do it anymore. And this process terminates, in this case, when I get to 1. So remember, that says that 1 is the greatest common divisor of 5 and 7. That remainder at the last step here. Because when I do it again, I'm going to get 0, and that means the remainder before is when I was done. So 1 is the greatest common divisor of those numbers. So now what we're going to do is we're going to go backwards. So now is where I'm going to look at this. So just look at this top equation. Solve that for 2. Solve that for the remainder. So that says that 2 is equal to 7 minus 5. And what am I going for? I'm trying to always keep this side as some expression involving my a and b, my 5 and my 7. Now what I'm going to do is I'm going to go to the next step in my division algorithm over on this side, and I'm going to solve this equation for 1, right? Because 1 is the remainder right here. So if I get 1 by itself, what would I do? I would subtract just to the other side. So I hope that you see this much so far. But then now what can I do? Remember that 2 is also some combination of 7 and 5, my A and my B. So I'm going to substitute that in for this 2 right here, and that's what we've done. And now what we'll do is we'll just see how many 5s and how many 7s do I have. Well, in this case, if I can highlight a little bit more, let's try. This would be positive 2 5s plus another one right here would be 3 5s, and then I'd have minus 2 7s. So the point then is that we just wrote 1, the GCD of 5 and 7 is 3 times 5 minus 2 times 7. So we've recovered, in this case, an x. Well, that's the same color. It doesn't do much for you, does it? We've got an x and we've got our y. That makes what? That makes the greatest common divisor able to be written as this linear combination. So that's what we want to practice. You do the division algorithm, but at each step of the way you solve for the remainder, and then you back substitute, always trying to get an expression in terms of whatever A and B are. So if we do a more complicated example, and what I've done too is because this example is more complicated, it is going across here, but it doesn't really spell out a lot of the addition and subtraction that goes in. So what I'm going to do is maybe ignore this for a minute and just come with me down here. So our A and our B are 130 and 61. And I think everyone's okay to just do the division algorithm until you get to a point where you stop. In this case, when the remainder is 1 here. So remember, this says that 1 is going to be the greatest common divisor of 130 and 61. Now what the goal is to write 1 equal to x times 130 plus y times 61. That's my goal. What are x and what are y to do this? And just to show you kind of step by step how it goes, what we'll do is we'll start with the first part here, and I'm going to solve it for 8. In other words, I'm going to try to get stuff with 130 and 61, my A and my B, on the same side. So this much tells me that 8 is equal to, 130 minus 2 times 61. What I'm going to do is I'm going to hang on to that fact. So now I'm going to come to the next one. I'm going to solve it for 5. So solve this equation for 5, and I see that 5 looks like it's, I would subtract this over. So 61 minus 7 times 8. But now what you'll do is, here's this 8 here. I can write 8 as another expression involving my two numbers, 130 and 61. So plug this expression in for that 8 here. And whenever you do that, it looks like 61 minus 7 times 130 minus 2 times 61. And then now, don't multiply that all out. Think about 130 and 61 as like being variables, and we're just going to count how many we have. So that in this case, what does it look like I have here? It looks like I have positive 14 61s when I distribute that through, plus another one would be 15 61s. So this is 15 times 61, and then what else have I got? Let's look at our other number. This looks like minus 7 times 130. And what I'll do is I'll check my work really quick, and that's what's, again, some of the work about where this line came from. It is a lot of this work right here. And again, I hope that emphasizes you're going to treat your numbers A and B, in this case 130 and 61, treat them like variables and kind of count how many you have. And so what we can do then is the next time that I see a 5, and you'll see that I'm going to see a 5 in the next equation here, so let's write it down. I'm going to solve for 3 first, the remainder. So 3 is equal to 8 minus 5. And now what I'll do is for this 5, I will plug in, and for that 8 for what it's worth, I'm going to plug in my expressions for 8 and for 5 that are based on 130 and 61. And so if you keep doing this all the way down, you should get 1 equals, and I'm just going to cheat a little bit. I know it should terminate in this process here. So it should be 23 times 130 minus 49 times 61. And again, the underlines are just to kind of emphasize what are the A and B the whole time, and also what is the remainder from the left side. So just so you see how those are always working. Okay. And then there's just another example with some extra notation. This is a little bit cleaner notation. You could use it if you'd like. You don't have to though. But this is the exact same computation as we just did. Again, just the notation on this side is a little bit different. Now Sage can also compute this stuff for us, and it's this command x GCD of a comma b. And what it does is, for example here, when you do x GCD of 5 and 7, the first thing it spits out is what is the GCD of those two numbers, but then it spits out what is x and what is y. So then in this case, this says how you should read this is 1 is equal to 3, that x, times the first thing, 5, plus negative 2 times 7. So Sage can compute what those coefficients are in the linear combination. And just to kind of verify too, in the example that we just kind of talked through, we saw that the coefficients should be 23 and negative 49 on 130 and 61. And so you see when you do this in Sage, yes, you get the coefficients are 23 and negative 49. So 23 is what you multiply 130 by, and negative 49 is what you multiply 61 by. When you add those together, you get the GCD, 1. So there's kind of a computer sciencey or kind of way to write this algorithm we just talked through. You can take a look at that if it makes sense to you. Otherwise, just rewatch how we did a few computations to get a feel for it. But what we'll do is we're going to use that now in order to compute the inverse of an element mod n pretty quickly. So what we'll try to do is, if I'm looking for the inverse of an element a mod n, I know that this exists exactly whenever a and n are relatively prime. So in particular, their GCD is 1. Therefore, what we're going for, I'm going to try to write ax plus ny equal to 1. I'm going to try to find my coefficients x and y here that make that happen. Just like we were talking about, if 1's the GCD of a and n, then I know there should exist an x and a y as the examples we just did. But now think about, I'm going to reduce things modulo n, right? Well, when I reduce modulo n, this is 0. So in particular, the point is, the x that you found, the coefficient on a, that is the inverse of a mod n. So let's go ahead and do an example with that first. So let's say I wanted to solve the congruence 17x is congruent to 1 mod 61. In other words, you could think of this as find the inverse of 17. So find 17 inverse in, z mod 61z star. So find its inverse there. It's another way to say this. So what we'll try to do, like I said, is we're going to try to write 17 and 61, write 1 rather, as a linear combination of 17 and 61. So again, as usual, on the left, we're just going to, we'll first divide 61 by 17 so that you can get your remainder, which is 10. And then now we're just doing the division algorithm. So shift stuff. So 17 is going to go here now, and the remainder is going to go here. Divide again, the remainder is 7. Shift one more time. So now 10 goes here, the remainder 7 from above one's right here. When I do the division, the remainder is 3. And I can do it again. I'll remove the, in this case, that should be a 7 right here. That is a typo. So 7 right there. And the remainder then is 1. And that is when this should stop. So now what we'll do is we'll retrieve our coefficients, x and y. And remember that starts on this side now. We're going to solve for this 10. When you solve for that 10, hope it makes sense where this comes from if you just subtract this over. And now remember the goal is to always write things on this side in terms of 17 and 61. And so I've got my 17 and my 61. And remember what this step does is it tells me if you encounter a 10, here's how you can write it in terms of 61 and 17. So in particular, when you solve this for 7, 7 looks like this, and you see you have that 10 there. Well, that 10 is going to be 61 minus 3 times 17. When you go through that arithmetic and you regroup like terms, you should recover minus 61 times 4 times 17. And we'll just keep doing that algorithm all the way down to the last step here. And then you get minus 5 times 61 plus 18 times 17. So your two coefficients are minus 5 and 18. So now remember, what are we doing? We're going to reduce things, modulo 61. So if you look at this and you reduce mod 61, that means anything times 61 is congruent to 0. Therefore, 18 is going to be the inverse of 17 mod 61. So again, x equals 18 is a solution to 17x congruent to 1 mod 61. So it's a solution, and remember, if I add 61 to that, that'll be a solution too, but in particular, 18 is the unique solution that's between 1 and 61. By the way, Sage is capable of doing this for you too, and the command for it is, we're going to set a to be capital M, and then what you should do is type the element you want, and what's the n, the modulus, and then you could just ask Sage, hey, tell me what a inverse is. You don't have to set a as like a variable, and so just to show you that, we could just type something like, oops, is my, no, it's not on right now. Oh yeah, it is. So we could just type in mod 1761, and then we could just tell it inverse, and it should spit out. Fingers crossed, it should spit out 18. Notice though that it's like a capital M. Notice that your element 17 goes first and that the modulus n goes second. I think it's just taking a while because I wasn't using Sage for a little bit, so it's thinking. It should pop up here. Normally it does not take this long. And it finally spit out 18. And so again, that is a quick way to maybe check your work in Sage.